Yes, hello. Good afternoon, everyone. I'm happy that we are back here and we can continue our sessions. And this session is called AI for Risk Assessment 1. But the point is the evidence generation, evidence synthesis, how to use AI methods to help us in generating evidence. Maybe it's the best way to describe it. And we have here 4 presenters today, so it will be a bit dense, but we still manage, I hope, to pull this off. So first, without further ado, I would like to welcome Rens van der Schoot, if that's fine. He works as a full professor of collaborative methods in AI and data science at Utrecht University in the Netherlands. He is the director of the AI Lab on AI-aided knowledge discovery and coordinator of the open source AS Review project, which is a tool which we also use. So that's kind of neat. So let's take it away. Here's your mic.
Yeah, thanks. And I'll put an alarm of 15 minutes, right? So to help you with. Okay, welcome. Find yourself a seat. Cool. Okay, my name is Rens van der Schoot. I'm full professor at Utrecht University. And indeed, some people are using our tooling AS Review. It's good to know that this is not a commercial tool. This is just something we developed in our AI lab. Unfortunately, I also have to leave after your presentation because my plane leaves at some point. Okay. So, what to remember from this talk? So I start with the end, right? Whatever task, there's never one perfect AI model. I think that's something you should remember from this entire 2-day symposium. So whatever you do, there's never one perfect solution. What's also evident after hearing all the presentations of these 2 days, you need data to test what AI model works best for your use case. So we're still in confusion. That was the conclusion of the previous session, right? So we're in a confused era. We don't know what AI model works best, so we need data, labeled data, and I will show you a lot of examples how we do that in our AI lab. And 3, open, 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 and open. Open source, open science, open sharing, everything open, please, open. And you already presented this previous session that the open source AI models are actually pretty good and maybe slowly taking over the commercial ones. So that's the conclusion. Open or open, yeah? I'm director of one of the AI labs at Utrecht University. That's the AI-aided knowledge discovery lab. And in this lab, we run all kinds of projects related to all kinds of societal challenges. For example, one of the challenges you sometimes face at the EFSA, creating an overview of relevant literature. And this can be for food safety guidelines, this can be for medical guidelines, this can be for PhD students who have to create a literature overview in their first chapter of the dissertation. Doesn't really matter what. It's always about screening papers or screening text data, not necessarily scientific papers, and to create an overview of the literature. We very much believe in fair data, so all our projects are fair. We apply natural language processing or AI or machine learning or whatever buzzword you want to use. I use AI to get grants, right? But in fact, it's just a logistic regression model, right? Sometimes. And then we also provide a lot of software tools and infrastructure. And be aware, this is not commercial tools. This is not software as a service. So this is but it is open source and it's community driven. Okay, we started back before Corona with some pilot projects and with some proof of principle projects. And then we helped a lot of people managing the number of Corona papers that were written. Remember those days. Also, our papers actually were used for the front cover of this Nature publication. Again, using all kinds of open source tooling and infrastructure to tackle this enormous amount of scientific papers. And this is basically the pipeline you probably recognize. You start with a research question, and the final goal is to come up with a systematic review. And it's not the task to find just one relevant work, and whether this work is a scientific paper or a policy document doesn't really matter. But the goal is not to find just one, but is to find all of them. Right, so I think for a medical guideline, you also want to find that one particular paper describing side effects for your child. Right, you also want to include that paper. And then there are a lot of these steps. And this paper, not written by our team, but this paper was published before the AI hype. And there are many different software tools because we find too many papers, right? So for all of these steps, you have an enormous amount of tools you can use. Yeah, make a photo, right? So yeah, okay, yeah. So you don't want me on the photo, right? Oh man. And this is before AI. So there are no AI hyped tools here. So this is before the AI revolution. So for each and every step, you have these options to use automation tools. And one of those is AS Review, the tool that we developed in our lab. Very nice overview. You nowadays also have these kind of overview papers, including all kinds of AI toolings. But I like this one preferably because it's not using AI, or at least the AI hype did not occur. I think you could now rebranch every of those software tools as an AI tool, which we also do. Okay, so here's the process. You search for a specific research question, you find a lot of papers to read. So 5,000, 10,000, I don't know, too many. But the task is actually to read all of them to find a few that are relevant for your particular research question, right? Recognize this endeavor? Yeah, I see people nodding like yes. And sometimes you look like this after screening so many people.
I always look like this.
So you never recovered from, so this was you and your PhD and then, oh, okay. Well, anyway. So now the question is, can we now not somehow use a machine to help us or take over? That's one thing we should discuss, help or take over, to actually find the same number of papers as that would have been identified by a human. Right? So that's a task. We want to speed up this process because we don't have the time, like with the COVID pandemic, or because it's too expensive, or simply because we just don't want to read all of those papers, right? So many of those papers are pretty relevant or close to being relevant, and that's fun, but there is also a lot of garbage in those kind of data sets. Okay, so here is how it works. You always have pre-processing, right? You have a research question, a search string, you have specific inclusion and exclusion criteria to make it systematic. That results in an input data set, and with an input data set, we refer to the records you want to screen. Maybe abstracts of scientific papers, or policy documents, or legal cases, or whatever. So the pre-processing ends in a data set you want to screen. Then you have an annotator, you. Because we don't want AI to take over the screening process, we want a human, an expert, or an oracle to actually do the screening. You're the expert. Yeah? Then we need to pick a model, and I will show you a lot of models if I still have time. And we always start with a training set. So remember, every machine learning model requires a training set. And what's the minimum training set you need for such a task? It's one relevant document and one irrelevant document. Because if you have 2 data points, you can already train a very simple model, like a logistic regression model. So you have a minimum training set. You can also use a much larger training set, and the bigger the training set size, the better the performance of the models, right? But the minimum training set is one relevant document and then one irrelevant document. Based on the training set, a model is being trained, and then the model can rank order all the papers that are not seen by the human. And the model simply presents you the most likely relevant paper. The human labels this paper because you're the oracle, you're the expert, and then the model has 3 data points. It trains again, improves the model predictions, it shows you the most likely relevant paper, and here you have the training cycle, and every time it recalculates the relevant scores, it updates the rank order, and it always shows the human the most likely relevant record. The human then reads this abstract, provides a label, and that's then added to the training set. And this is a continuous process. And this is what we call active learning. So far, so good? Okay, nice, cool. An example, so this is one of the bigger studies we do at our AI lab. We're trying to come up with studies and protocols and help for people who are suffering post-traumatic stress because of natural disasters, because of school shootings, because of being veterans and witnessing war trauma. So we wanted to create an overview of the existing state of affairs, describing trajectories of post-traumatic stress after such an event. So nothing related to food safety, but it gives you a nice overview of the task. So I identified more than 6,000 records, of which only 38 appear to be relevant for this particular use case, right? And that are the numbers that we're often talking about, right? 5,000 papers to screen to identify only a handful of papers. Okay, now exam question. So in this session, you do get exam questions. So here we have 5,000 papers on the x-axis. I start labeling those papers from left to right. How many papers do I need to read classically before the AI revolution? How many papers do I have to read to actually read and find the 38 relevant ones? All of them! Yes, indeed! Because every now and then you will find one of those relevant papers, right? But you have to read all of them. Assuming that you never become tired, you will always find the 38 relevant ones, right? But you have to read all of them. Now the question is, with active learning, where all the papers are rank ordered according to their relevance scores, how many papers will you need to read? So on the next slide, we'll see two people. One person will read randomly, that's the gray person, and one person will read with active learning, that's the green person. You will see a dynamic graph, and it starts all the way up here, and then the person who's done first gets a trophy. Right? So here we go. This person, yeah, first relevant paper, second relevant paper, we're at 300. Oh shoot, the other one is already done. Wow. So by re-ranking all of those papers, so presenting the first relevant papers, the relevant papers first to screen, results in much better performance than just randomly screening. Okay, this was my data set, right? So the models are optimized to actually do this task using my data. No. But a couple of years ago, we also conducted these kind of simulations for data sets from the EFSA. So I was given, I think, 15 data sets of food safety guidelines, the systematic reviews then behind it. And for example, here there's one, here there's one. So I'm not familiar with the content, right? I'm a statistician, so I have no idea what this is about. Yeah, something with cows, because that's using those abstracts a lot. So here we have 4,960 abstracts, of which 34 were relevant, according to experts from the EFSA. Here we have a similar recall plot, and as you can see, also for this sample, already after reading a couple of hundred papers, all of the relevant ones would have been found, or in particular, only 274 papers would have had to be read instead of close to 5,000. That's an enormous time saving. But again, I cherry picked because this was the best performing data set. Remember, I had 15 data sets. So we did all of these simulation studies, and as you can see, for some of the data sets, it worked rather well, but for some other data sets, the performance was not so good. Well, if you summarize that in a table, here we have the work saved over sampling at 95% recall. So 95% of the relevant papers are found. How much time could you have saved? And you can see that for some of the data sets, the screeners could have saved a lot of their time. Whereas for some other data sets, the time savings are less. But it's always more than just random reading. Okay. Then the question is, what model did you use, right? This is about open data and open data. So, okay, we actually use naive Bayes and TF-IDF. For the people who are familiar with that, they will probably recognize that. And that's the red line over here. So here we zoomed in on the first part of the recall plot. But we also tested many different other models. And as you can see, that depending on what model we choose, the performance actually changes. So if you select this model, this gray one, you still have to read close to 3,000 papers. But if you would have picked the orange one, well, what is it? Logistic regression and SBIRD, for this data set, you were already done after reading 500 papers. So it matters not only what data set you use, but also what model you selected. Okay. So what we do in our lab, we also provide all kinds of open data sets. So this is a collection of 26 labeled data sets. Some people are using it, well, almost 2 million downloads. So this is one of the new standards in benchmark testing. So here we have 26 labeled systematic reviews from all over the world. So we were just scraping for data And with data, I mean the records screened for a systematic review. Oh, yeah, photo. And you really don't want me on the photo? No. Oh. And here you can see on the next slide. Yeah, here you see the data sets on the x-axis. And on the y-axis, we again have the work saved over sampling. And this is a summary of more than 20,000 simulation studies where we varied the training data and we varied different statistical models. And as you can see, for example, for this whole data set, no matter what model you picked, no matter what training data you used, you always save an enormous amount of time. If you, for example, look at this data set, well, Jeremiah, it matters a lot. So there's a lot of variance. So depending on what prior knowledge you select, depending on your statistical model, you can either have, well, a very good performance or an excellent performance. And for some data sets, the performance is close to random. Just again showing it matters what data set you use, how well the model performs. Okay, we can also turn it around. So here we combined many different models. If you have questions about what models, then I'm happy to answer those, but it doesn't really matter. So we have all kinds of models, and the task here was to just read 100 records. So let's say you only have 1 hour to screen. Which of the models could then identify most of the relevant records? Well, it's apparently this one, random forest with MXBy, and MXBy is like a large language model, or a small large language model, so to say. It could identify most of the relevant records across all of those data sets, but the disadvantage is this model needs about 5 hours training time. And if the task is to screen only 1 hour, well, if you have to wait for 5 hours before you can screen, then with a lightweight model, for example, TF-IDF, and just a simple logistic regression model, you could have already found many relevant papers. Okay, what if the task is to find the last relevant paper? So this is the hunt for the last relevant record in the data set. So you've already screened for many, many, many hours, and there's just one more paper to find. Well, then apparently, this MXBy model outperforms all of the other models. Probably because it's based on a lot of training data. It's pre-trained, right? So it understands context. And this last relevant paper is probably a little bit different compared to all of the other data sets. Okay. So instead of one model, there are a lot of models. But then again, many of these models are maybe closed source. So what we want is actually we want open models. Why? I'm going to show you that on the last couple of slides. So this is one of the papers we've written about why reproducibility and transparency is of importance, but it also has a downside, data storage. So if you put this on a dimension where we have a black box model on this side and where we have an open model on that side, if we ask, for example, ChatGPT, what we also do in our AI lab, so well, you cannot read it, but that doesn't really matter. So we have a prompt asking ChatGPT to screen all the papers. It gives us output. It gives us reasoning, it gives us explainable content, etc. So done. Within half an hour, you could screen how many papers? 5,000 papers. But it also makes mistakes, right? Some papers are not identified by a large language model. We use ChatGPT, but it's a black box, so we have no idea what the training data is of ChatGPT, etc. Okay, so maybe we need to be transparent. What kind of model we use, etc. So here we have a list of all kinds of software tools that implement active learning. How are we doing with the time, by the way?
Fine.
Fine, okay, perfect. Yeah. So here we have an overview of software tools that implemented the screening prioritization. And as you can see, only 2 are open source. That's our tool, but also FastRead, and all the other tools are closed. That's not necessarily a problem, right? Depends. Do you want to see the open source code? Well, the least you should do is be transparent about what kind of models are being used, right? So we also try to find out what the models are that were used by those tools. And for some of those tools, we could simply not find this information. No. I mean, that's the least they can do, right? At least tell us what model they used, right? Maybe they cannot show us the training data, or maybe they cannot show us all the code, although I still believe in open source. But this is the least that they can do. So transparency, that's the minimum requirement, I would say. Reproducibility. So remember that we're having this training cycle and this labeling cycle. So humans produce data, the labels, but machines also produce a lot of data, predictions, relevance scores, probabilities, parameters, hyperparameters, many of those things. So what do we want to store in this process? So to make it reproducible, we should store as much as possible to reproduce this training cycle. And here's a balance, because what do we want to store? So this is what we store. So we have all kind of data like labeling time, the labels, the rank orders, the predictions by the model, what model produced what data. But at some point, are we going to store everything? Because at some point, it becomes terabytes of information. So this is a very complicated balance. So black box machines like ChatGPT give us a lot of results in a split second. We need transparency. Does it also have to be reproducible? I mean, every time you query ChatGPT, it will give you a slightly different answer. But what do we then need to store to make it fully reproducible? And this is an open question because we don't know, because this is the area of confusion where we still are. We want to store maybe everything, but if that's a terabyte of information, at some point we have to stop on this dimension. But then the question is, where exactly? And this is actually my question to you. What do you think about this dimension between, on the one hand side, being a black box, easy, quick results, or store everything, which is maybe not feasible because then we need terabytes of data storage? Where do we want to be? Where do you want to be in your organization? And then we open up the room for discussion.
Thank you. I will just take the mic. Thank you very much, friends. I will not answer that question.
Why not?
I will let the audience answer first.
Smart. And so I have to leave after this presentation. So also if you have a question to me, either ask it right now or do send me an email later. That's also fine.
I think Eileen was first, but it's
Thank you. Eileen O'D, EFSA. My question is about when you're showing those comparison of reading all the papers versus when you reach all of the relevant papers, you're obviously looking retrospectively when you already have the answer of 38.
Yeah.
So my question is, how do you decide when to stop and to know that you have enough without reading all 5,000?
Thank you so much for this question. This is what we call the stopping heuristic. At some point you have to stop, right? So you don't want to read everything, but you also don't want to stop too soon because maybe you missed that one relevant paper. If we solve this, we can publish in Science or Nature today. So this is an unsolvable issue because, yes, this is done by hindsight. So we know how many papers are truly relevant. And still, we rely on humans who provided all these labels. So there are also human mistakes in these data sets. So what we do in our AI lab, we sometimes relabel data sets. And we even find mistakes made by humans, right? Due to screen fatigue, for example, right? So question one is, can we really trust the humanly labeled data? And now we're questioning, can we trust the rank order produced by the machine learning model? So for example, one stopping heuristic can be 50 irrelevant papers in a row. Because remember, every paper that you see is the most likely relevant paper. So what if there are 50 in a row and you're still seeing irrelevant papers? So 50 in a row, take this gray line, you would have stopped here. Not finding 1, 2, 3, 4, 5 of the other papers. So this is balancing being conservative and saving as much time. So the next question is then, this last paper over here, is that truly relevant to your research question? Does it contribute something new to all the other papers that you already found? So this is like information retrieval, an information retrieval question, right? Does it add something? Maybe yes. Then the next question is that one relevant paper actually already in the data set? Or did you miss it because you searched only in Western databases? And you did not include the Chinese databases that we heard about this morning, like China is producing many more papers than we do. So if you do not search in Chinese databases, your relevant papers are maybe not even in your data set. So your question is actually a very difficult one. And yes, you have to think about that. When to stop screening with active learning. The same with using ChatGPT for taking over the screening phase, right? So do you trust the results by ChatGPT, or do you still want to double check some of the results? And maybe sometimes you're happy if you already have 80% of the data because you need to publish this guideline today or this week. Maybe you have plenty of time, and then it doesn't matter how much time you take to also identify the last relevant one. It's a balance.
Yeah, thank you. We also use this kind of heuristics, so consecutive irrelevant papers for stopping. It depends on the time
42.
what we have. It depends on the time.
42 is better.
Yeah, 42 is always better.
Yeah.
There was a question here, and then Anna.
Thank you. I just want. I think I saw in passing the citation standardization of citations, and it triggered sort of what are actually the parameters for making this relevant, and is this different from how humans would choose and how the AI chooses, or?
Yeah. So with active learning, I'm just going back to to this. So with active learning, it's all based on the training data that you enter. So if you start with a relevant paper and an irrelevant paper, the machine tries to understand what's the difference between the two. You can also start with the inclusion criteria and the exclusion criteria. You can also start with a historical published systematic review. For example, if you want to publish an update, right? So every 5 years you want to update your systematic review, you can use all of your original data. But it all boils down to these inclusion and exclusion criteria for this task. And these criteria have to be set before you actually start screening and have to be consistent over the screening phase. So you cannot learn throughout the process. That's the same for using ChatGPT. So you cannot read it, but I guess we will share the slides at the end. But also in the prompt for ChatGPT, all the inclusion criteria have to be explained in great detail, because otherwise ChatGPT cannot come up with the reasoning why a certain abstract is or is not relevant. So the trick are these inclusion criteria or exclusion criteria, because you're not interested in, I don't know, in animal data, but only in human data. Yeah?
Thank you. And one last question. A short, easy to answer.
It's not even a question, because I think she asked the question that I had already, which was about how do you classify what's relevant and not relevant. And that had to do because, of course, I saw some of the outputs from the unit I work. My name is Ana Afonso, and I work at EFSA. They were on the top, so I'm very happy for that. But I think it has a lot to do with that. But it was more about your final question, so it's more of a comment. Yeah. Your final question was about store everything or black box. And this is, I guess, the big question for all of us that work on regulatory risk assessment, and very tough choices have to be made in terms of time. So my unit in particular, I've been working with systematic reviews, real systematic reviews, because a lot of the work that is done on literature reviews is not systematic reviews.
You.
And there we're talking about almost 5 years of work with a large consortium providing data, and this was done for upper levels. Is it worth it? And I think that's the question we need to answer. Is it worth it? Did we gain anything with this time investment? So it's a really, really difficult question, and one that I think a community such as this would help, because there is no easy answer. I also work in my unit with GMOs. So in GMOs, we are not scrutinized. We are double scrutinized, triple scrutinized. So if we miss any information, there will be a problem. So we need to be reproducible, absolutely transparent, and we need to store everything. Yeah. So I don't think there will be an answer, one single answer. One of the things I liked very much about your presentation was, can we establish minimum criteria for the acceptance of certain models or acceptance of certain tools? We use Distiller in EFSA for many years. We use a lot of AI inserted into Distiller. We did a lot of work in labeling and tagging to be able to improve it. But I was surprised you couldn't even find what is the model behind. I was like, oh my God.
Yeah, but do let me know. So I really want to also to challenge you to help me get rid of these question marks, because I tried to search in their documentation. I couldn't find it, but it's also maybe my misunderstanding of something.
Well, we'll get in touch with you because I think we have a
Yes,
large contract
please.
with them. We should be able to force them
Yeah.
into it. No, but
Exactly, because especially now with the European AI Act, you have the power now to force them to open up their black box. And the question is, how far should they go before they can satisfy your requirements? But two small comments, because I think the output of a systematic review is not only the set of relevant papers and the data extracted, it's also consensus among experts, right? Don't underestimate that part. And I think what is really important here is that we, the humans, we should stay the experts in the oracle. So yes, the AI can help us, or maybe you will combine human screening with AI screening. So for one of our projects, we were done screening. We asked ChatGPT, can you screen the papers for us? And we found 4 more relevant papers that we simply overlooked because the text was so different that we did not recognize the relevance of those papers. So you can also use large language models and these kind of tools to improve the quality. So not replace screeners or replace processes, but improve the quality, especially in these kind of use cases where you cannot miss one study.
And I forgot to say something. Thank you. Really great presentation.
Yeah, thanks.
Yeah, thank you.
Okay.
Thank you, Rens. Yeah, an applause. Oh,
Nice, right?
thank you. I would love to have more questions, but we need to run. Yeah, no. Sorry for that. Yeah, thank you very much. Thank you very much. So I would introduce now our next speaker, Tome Eftimov from the Computer Systems Department at the Jožef Stefan Institute in Slovenia. His research interests include statistical data analysis, meta-heuristics, natural language processing, representation learning, meta-learning, machine learning, and yeah, just take it away from here. Thank you.
Okay, thank you, Akos. Hi, everyone. So I'm going to speak food data information and relation extraction, lessons from the past and AI challenges shaping our future. So what to do next when we have these 42 relevant articles? Now we screen everything. We have these 42. Do we need again to read them? Because it's again like a lot of time. We don't want to read them, but we would like to find all the relations related to food safety, security, food concepts, relation with biomedical entities, chemical entities, create this knowledge bases, what people are using buzzwords like these 2 days, retrieval augmented generation, large language models, how should be plugged. So actually we need to provide like a lot of external resources, right? And then we can start using some of the most powerful like AI models. So today we are going to talk about food data. I'm going to talk about text data. So food information extraction, food biomedical relation extraction. I will present you a foundation model, which is large language model trained only to work with food data. And you see like how this is related with semantics, everything we speak during like these 2 days, and what is next. So actually, before we start, I have one question yesterday on the panel session, because I said if EFSA is interested only in food consumption data, because it was like with Akos the discussion with these unusual data sources, right? But from as computer scientist, I'm not interested in unusual data sources. I'm interested in data. So from farm to fork, I understand about like, I don't know, we have like some sensors data, we have lab data, biomarker data, we have a lot of evidence which is presented in text, in scientific articles, evidence-based data recommendations. We have a lot of apps which are available, right? So somehow we need to link all this data, and when we have like this knowledge, we can have much more better models, and we can have like even much more powerful answers, right? Why to treat all studies in isolation, okay, only food consumption data, when there are other environmental factors that are actually influencing the food consumption patterns? And this is something we need to take into account. And it's not about food consumption data. It's about like all data which is relevant. And it was the question, okay, what if we are missing some part? How this AI model will work? So we need to think about, okay, multi-view, multitask learning, continual learning. So it's not like a static AI model, but we need to be aware of what is like AI power which is behind. So as I said, today I'm going to talk about only like the food information extraction, because there is a lot of things. So I'm focusing only on the text data. Now we have these 42 articles which are screened. We got as a result. Thank you, Rens, for a really nice introduction. And now we need to find what is inside, right? And when we think about like the information extraction, we have like name entity recognition, which means like, okay, we have this text, so we would like an automatic way to find like what are like the food concepts, what are, for example, the biomedical concepts. Here we have excessive salt intake has been associated with a higher incidence of heart disease. So we like heart disease and also salt to be like automatically discovered, recognized. And then is this enough? No, for sure. Why? Because, for example, think about we can have different languages or even we can have some chemical Latin names of the same entities. And for the computer, it's really important to know that these two are synonyms or the same things, the same concept. So what is the idea? Here we have the semantics, we have the ontologies, right? So we need to plug them into here. So what we need to do is every concept which is recognized, actually we need to link like to some ontology that exists. There are several discussions. We need to build a new ontology and everything. No, we don't need to build new ontologies, people. We just need to reuse what exists. And then you don't need to use only one. You need to use several of them that are already, because you need just to make your data interoperable. And then what is the idea? You will see in the next slide. Here, there are some artificial IDs which are provided. They are not true IDs. In the food domain, we have the food exva, which is by EFSA. To be honest with you, it's really nice only for food consumption data, but if you want to do something which is related like with biomedical entities, for sure you need to do SNOMED city ontology or food on. Or at least you need to have a way how a FoodX consumption study, which is actually labeled with FoodX annotations, can be transformed automatically to SNOMED city and the other, which was also one question when we said if these terms are related together between different ontology, and the answer was we need joint work on this. But I'm completely honest to you, this was already done in 2018 and 2019. So there are resources, and I really like people to be aware of what exists and not reinventing and rebuilding the things that exist. So now we have from language technologies to decision support, right? Why we are doing this? We are screening, we are taking relations because we would like to ask questions like chatbots, and then we would like to have this knowledge, right? And we start like this. We got like the 42 articles. We recognize the name entity recognition. We do the name entity linking, maybe some relation. If, for example, a food is good for some disease, can be used as a treatment or cause, like can actually cause the disease. We got some relations. We have some knowledge base, and then we can do whatever you want. Now with the power of large language models, you can do even retrieval augmented generation. You can do like a lot of things, like even you can find you a large language model if you want there. So what's happening? Now let's go to the biomedical domain first. And if you go from 2004, here I have till 2021, you can see how people annotated data. They said 2004, we will do only gen mention in the text. So people went through the screen, they annotated, they put like the labels from an ontology. Then 2006, again, gen mention, then you can see protein, chemical, drugs, everything. And they have like standards which are common for which they can share data. And people who are doing text mining at that time, they can use like these data and they can train models to recognize them. But you can see that this was like really time-consuming process, like really difficult, right? But it has results that then people from biomedical domain can do a lot of things compared to the people from the food science, which are, in my opinion, talking, let's do some changes. So what is happening now? If you go to the clinical domain, again, they are like this, I2B2, disease drug treatments, electronic health records. And why this is possible? Because we have this unified medical language system. I can say for me it's a catalog with all existing ontologies, with all possible tools that can be used. And for example, from the advisory group of data of EFSA, I'm expecting such a catalog to be available because at least pointers where these tools can be found. And now, if I go like again to the biomedical domain, in 2020, we were somewhere here. If you go to the food domain, we can only detect some food entities and also food or not food, not thinking about linking them to the ontologies. And then here you can find a lot of resources. These are from our group, starting from 2017 to 2022. Different color is actually if this is a name entity recognition, if this is like a relation extraction or is a semantic resource. Maybe I can tell you something about this food onto map. This is actually a resource where food on, FoodX2, SNOMED city, onto food, different ontology that already exist. If you have a data set which is actually labeled with food on, how automatically can be transformed to food X2. So this already exists. It's a few TXT files, everyone to use them, just download, find the code, and the codes are linked each other. So we don't need to think to reinvent these things. Okay, new ontologies which are coming can be easily added there, but something already exists. And just I want to share you this food name entity recognition that work with recipe data, instruction of how to prepare recipes. If you look in the results, like some F1 score for the language models at that time that were famous, BERT, BioBERT, and BioBERT Standard, BioBERT Large, and BioBERT Standard, you can see we have around like 75% of F1 score. So this means that we can find somehow, we can link to some of the ontologies, to food on, to hazard, so automatically we can find these, how to say, labels, like what are the labels from the ontology. So we can find that this is a pizza and what is like the food on actually ID for pizza. So this somehow works, but it doesn't work with scientific articles. It works only with instruction of recipes, because if you have different writing style, your model is actually biased to the writing style, right? And at that time, in 2021 till 2022, I got to be a scientific coordinator of this cafeteria, which was EFSA funded project. And it was really nice experience. And I really like what Ren said at the beginning, the 3 take-home messages. It's about data, data, and data, and provide label data to test your models and everything. And then at that time we say, okay, till that time you see like what happens in the biomedical domain, right? But the food domain, no annotated data. So we need to start from somewhere, right? We need to provide like this data. This was the cafeteria project. It comes with 2 corpus, food composition database and scientific articles, and then we label them with regard to all possible ontologies. We create these data sets, and these data sets actually we shared with the BioC format for data sharing in the biomedical domain, which is common. And I will be completely honest to you, we have the best project manager from EFSA, Hermano, but we have really difficult discussions to convince people from EFSA that this is the right way of how things should be done. And now, when we come here, we have also this, how to say, combination of models. What Ren said, one model is not the best one. You need somehow to have more models. You need to combine, and this works perfectly. It was publication, data set available, the project ended successfully, and everything. And at that time, we said, okay, this project ended. We have the first food data corpuses. People from AI who are doing like food natural language processing are happy because they can benchmark their new methods, and everything can finish there, right? And now I can tell you something like this. With this, after having like these data sets, we can do something till here. We can even find relations. I'm not going to show you today, but they are like really nice publications that can do together. So we have some database. And then, okay, but now large language models come. I need to benchmark them. I need to see if they are actually efficient, right? Okay, we have these cafeteria data sets. EFSA give us money, we provided them. Now we can see if they work, not to go to panel and to talk about that there are a lot of large language models that can be used, but let's see how they actually work. And then these are the ChatGPT 3.5 and 4, and they are just benchmark if they can recognize between food and non-food entity, not labels, not think about to distinguish between them. And you can see the accuracy. These are like different data sets from cafeteria, depending like food ons, nomad city, and so on. And these are scientific abstracts here. Here you have like the food consumption data set. And do you know like what is the accuracy if you ask, okay, find the entities, but also give me the food on labels for the entities? What do you think is the accuracy? 0. Why? Because this data is not available. How people that train ChatGPT models have access to this data? Okay, cafeteria is open. It's the BioC format. It's actually EFSA deliverable. EFSA also has like this data set, but it's simply not used there, right? And then we have 0. So now all talks were, let's use large language models, let's use. This is like a proof of concepts. We use them. They don't work. And now if you go here, this is what is coming soon. And to see why cafeteria was really, how to say, important projects. And with this, you can see like the long-term impact you need to describe in your research proposals. Why? We have these 2 data sets. We perform multitask fine-tuning of open large language models, Mistral, Llama. We don't know which will work the best. We train them to recognize entities, food entities. We train them directly to link them to all possible ontologies that exist, like Foodon, SNOMED, City, and everything. We also ask, for example, I'm going to the fridge. I will mix these few ingredients with these quantities, what are actually the nutrient values for the macronutrient, and provide me if this is like a health or not health based on the food traffic light system. And then for these two tasks in the data set we use for training, cafeteria actually plays a crucial role. Without these data sets, we can still have zero accuracy in these semantics and ontologies. And now, if I show you some results, this is linking to the Foodon. ChatGPT, zero accuracy. You can see these are only different testing data just to see the robustness of the model. Look what is like the F1 score, 95% accuracy. And then if you think about nutrient value, and also you can have for SNOMED, City, everything. We didn't do for FoodX2. If you want, this is a simple seminar work. We can do this in 2 hours. And then if you think about nutrient value prediction, these are like saturated fat, carbohydrates, proteins, everything together, aggregated across all of them. Look in the F1 score. If you ask ChatGPT, you will get the answer. But it's a hallucination, right? It's not true. And then if you look in this food traffic light system, these are like some nice percentages about the classification, if this is a green, orange, red, and everything. So what I want to say is actually, without cafeteria, we cannot have like this. So now think about this model will be open. It's coming soon. It will be also interface, API, whatever. Everyone can use them. You can use like to do the linking to Foodon, to SNOMED, City, to whatever you want to do for this semantics. And maybe like this is the last slide. What else we are working a lot? Missing value imputation in food composition databases. Today I'm not going to talk about tabular data. A really nice publication also on this topic. This is the information extraction. I'm much more interested in the math which is behind, not so interested to bring this to the end users. But to be honest to you, like this linking between ontologies, you have FoodVis, also like in the footnote you have, this is supported also development by EFSA, by Cafeteria project, where each term which is recognized, you can also find to different ontologies direct link to the ontologies. So this is available. You just need to go there, upload your data, what Ren said, select several models, automatically find everything, linking everything, got like the results. So this everything exists. I think that no more data, it's better performance, but selecting representative data, training data will bring you much more better results. So here you can see how you can predict macronutrient values. Working a lot with image data, for example, finding branded food, if this is like Nutri-Score A, if it is sustainable and everything, because you can extract, we have a lot of them. These are the relation I'm not going to talk about. You can extract all these entities. And then I got a lot of questions, like when we are doing this cafeteria, but this work only for food and this work only for food. Yes, people, because for chemical genes, proteins and everything, it's already developed. Why to reinventing like hot water, like warm water? I just need to reuse this. But the missing part was the food, right? This is what we cannot do. And this is the first knowledge graph, which consists actually the food, really nice. And also we are working a lot like explainable, what are the most important factors that are doing risk assessment. Besides all these things, we are doing a lot of foundational computer science, automated machine learning. If you have your data, for example, thanks to Ren's benchmarking data for systematic review, to tell you in prior, which of these models will be the best version for you without testing all these possible combination of models. So this is automated machine learning. This is the team which is working on this. And as I said, like a lot of projects which are already a lot of institutions, we were part of it. And if you have questions, just contact us.
Thank you. Thank you, Toma, for the presentation and also for keeping time. Hi, Rens. Safe trips. Questions? Questions? Oh yeah, okay. So it needed a bit of time.
So I know that, and I work at the Dutch Food and Consumer Product Safety Authority, and we spend a lot of time indeed trying to map between different kinds of entities, and also mostly open text fields. So this might be a dumb question, but what we have is, you know, a bunch of food inspection data that is in Dutch and written in a million different ways. There are lots of different ways to spell the same product, it turns out. And I have colleagues who spend forever trying to harmonize that and get it into some format that EFSA will accept. Like, is this going to help? And what would I need to do? I mean, I'm
I think it can help. It can have some noise in the results. So I always said like this can be semi-automatic, and then you can check. The idea is like we always work with English description, right? For example, even for us in Slovenia, we need to code like the EFSA food consumption study with FoodX2 codes, right? Now we tested some of these solutions. So what we have done first, we translate like Slovenian to English, and then we reuse this. At the time of 2015 and 2016, still the translation was not so good. But currently, with the power of large language models, this works really nice. So if you have like the Dutch version, just translate them to English with some open LLM, Llama 3, Mistral, whatever. They are all perfect for translation. And then once you have this, you just use like this LLM, which will be available, or even like some of the other models. You can use this FoodViz tool. I can share like the contact, and then you can get like all the codes. Like not only FoodX2, like food on SNOMED, City, everything what you need.
Yeah, thank you. But it's also one of the big questions for our domain, the different languages and the precision of the translation of large language models. In case of like classifying foods, it does make a difference how the translation, how well it is done. But yes, this is one kind of a future solution to this. Eileen, you want?
I had a very practical question about you're advocating that we need to put more effort into getting some of this data encoded to get it linked. Are there projects or proposals on the table that countries can join into or sign up for to try and build this body of coded?
As I said, like at that time, 2021, 2022, we did only this like for name entity recognition. And then as a proof of concept, we go beyond where we have done this knowledge graphs where we link like chemical, disease, drugs for the cardiovascular events, because we have access to medical doctors to check everything manually, like this kind of linkage. Now there is also another tool, which I didn't share today, but actually there is an opportunity. You can say, I'm interested, I don't know, relations between food and some allergy, right? And then you can use like PubMed API to find like a lot of abstracts. You can set, I want 1,000 abstracts. It's nothing about systematic review. So this is like a random screening. And then the idea is, can you find all possible relations between them? You can use this commercial LLM, this open element, open science, and also you can use some of these BERT, like much more small language models that exist. You just select and you got all possible relations in a table. As an expert, you just need to select them. For all these which are actually extracted, you have all possible abstracts from where they are coming, like traceability. So to help you, like as an expert, to see if this is really correct. There's another thing. Sometimes relations are not there because we didn't have in the screening data set, we miss a paper, right? And then what we are doing is a little bit graph learning, which is actually we are predicting link between a food entity and a disease entity, because maybe we miss because we don't have a paper there. And then for all of them, which we predict, we have what is the probability, and also try to find like PubMed abstracts that can help you. These are not extracted relations, that are forecast, like predicted relations, to help you to see what is happening behind. But there is a tool, it's easy, I can share with everyone, like you can start using, it's free.
Thank you, Tome. Also, I think that's a very valid question in terms of advisory group on data. Shall we promote like this infrastructure foundation, so preparing annotated data sets of different kinds, or at least facilitate these kinds of projects? Yeah, thank you. Thank you, Tome.
Thanks.
Once more. And now we will have two online presenters, and I would like to kindly ask Michael if you are here to show up. And so it will be Michael Sebek, and he's associate research scientist at the Network Science Institute with Dr. Albert Laszlo Barabashi. He works there in Boston. Hi, Michael. And his research is at the intersection of food science, data science, network science, and he's studying biochemical complexity of food and the relationship. Yeah, can you hear me?
Akash.
Julia is
Yeah.
supposed to be next on the
Yes.
schedule that we got.
It's not a big deal. Don't worry.
Okay.
Up to
So
you guys. I
hello.
mean, I'm already sharing the presentation. Hi, can you hear me?
Yes.
Hello.
Hi, Julia. Then I will introduce you as well, if you don't mind.
I can introduce myself, so we can just start,
to save
right?
time. Okay.
Yeah.
Then Julia.
Yes, there you go.
She's not Michael.
Hi.
Yeah.
I'm not Michael, first of all, but Michael and I work together. So hi, everyone. It's such a pity not being there. I would love maybe in the future. So my name is Giulia Menichetti. I'm a junior faculty at Harvard Medical and an affiliated faculty member at the Network Science Institute at Northeastern University. I've been leading a project called Foodome between Northeastern and Harvard Med that aims to track the full chemical complexity of the food that we consume and understand its mechanistic impact on our health. But now this project has spread all over the different layers of the food systems, reaching also public health intervention driven by AI. So a little bit about me. First, I'm not a nutritionist. I'm not a food scientist. I'm a physicist by training. And before leading this group, I studied statistical and computational physics, and I specialize in network science. So I'm a theoretical physicist. So let's move forward. So this is a historic slide for me. I put it everywhere. It's a motivational slide about why we're doing what we're doing that I periodically update with novel details. So despite things are slowly getting better here in the US, we have now the food is medicine movement. Nutrition is still out of the picture in many medical discussions. However, nutrition, as you can read here, is a leading factor in the #1 killer in the US and worldwide. So that is heart disease. And overall, only 10 up to 20% of US deaths are of genetic origin. That unfortunately is also the main focus of attention. Furthermore, according to a 2021 report on the true cost of food published by the Rockefeller Foundation, the US incur yearly $1.1 trillion of food-related health costs, with direct and indirect costs basically for CVD and hypertension leading the statistics, and followed by obesity and overweight. Last but not least, if we move away for cardiometabolic health to cancer, since the 1990s, there has been a rising incidence of cancers of various types among adults aged 50 and younger worldwide. Yet, I would say that this incidence, compared to the incidence of the incidence of hereditary cancer compared to the other cancers, has remained unchanged, suggesting that cancer is largely influenced by environmental and lifestyle factors. So we were inspired by the Genome Project to look into the building bricks of human nutrition. And for us, the building bricks are food molecules, and particularly food small molecules. Given our initial expertise in network medicine, we had expectation for food molecules very similar to what you find for drugs. That is, extensive records describing their presence in food with quantified amounts and interaction with known protein targets. Well, we soon realized that this scenario was very far from reality. We were a bit delusional somehow, and we collected our initial insights in a perspective piece that you see here, where we define for the first time the dark matter of nutrition. And we describe this as basically all the chemicals present in food and largely invisible to epidemiological studies, but also to food composition databases. At that time, in open source databases, we found approximately 26,000 compounds sparsely distributed across different foods. And by combining a variety of different machine learning tools, some of them you also seen today, from text mining to genomic predictions, we recently reached 139,000 chemical compounds. And of course, we keep growing. Let me give you an example for garlic. So the 69 nutrients currently documented by the USDA SR Legacy database, so one of our national databases, include vitamins such as ascorbic acid and essential amino acid like as alanine. Yet the database does not track important organosulfur compounds like allicin and arginine, which are, let's say, key drivers of the cardioprotective and antimicrobial effects of garlic. But also, for example, if we talk about polyphenols, so a class that is a little bit more studied, the picumeric acid is one example that is known to be protective against carcinogenesis and inflammation. So these are just 3 bioactive compounds of the more than 6,000 molecules that we have documented in raw garlic, many of which are secondary metabolites of plants, acting as the plant chemical defense against stressors such as predators and also extreme weather conditions. So the 2024 update of the Food On Project has been recently published in the Annual Review of Nutrition. This is a 10,000 words piece, which is a great bedtime read. And we discuss here several applications of AI methodologies, from helping to annotate untargeted mass spectroscopy to predict and validate targets for food small molecules. And finally, we give example of novel application of natural medicine to food compounds. So let's take a closer look to this library. This is a preview of some of the pictures that are currently under review in the New England Journal of Medicine. Well, by now, everyone knows about ChatGPT. It's not just about human language model, it's also about chemical language models. So chemical language model like Moleformer, which represent each food molecule as a vector embedded in a high dimensional space, allow us to visualize the structural and functional similarities of food molecules in the NutriDark Matter database that we usually call the NDM. So we have many lipid-like molecules, more or less, as you can see here, more or less 39,000, and also a lot of secondary metabolites of plants. Mainly the biggest class is phenylpropanoids and polyketides, that is around more or less 14,000. Then we have alkaloids, lignans, and neolignans, organosulfur compounds, and all these points are color-coded according to their subclass, and specifically we are reporting subclasses with at least 500 compounds, so there is much more. And on the right, well, here, you can see basically where all chemicals tracked in garlic sit, and in particular, the 3 chemicals that I mentioned before. So rather than behaving as the standard macro and micronutrients that serve as energy sources, for example, providing essential amino acids for growth and repair or regulating enzyme activity, many of these molecules in the NDM may be closer to drugs. So here I added on top of the previous map, basically all molecules documented in drug bank, and 24% of these molecules appear also in the NDM, implying that they are molecules, that we find in natural ingredients that we consume every day. For example, let's look at this part of the plot. So rosmarinic acid, a polyphenol known as antiplatelet agent that is not tracked usually in national databases, but for example, you can find in the Phenol Explorer, sits relatively close to a synthetic antiplatelet agent that is clopidogrel. So we see that the drug compounds that are basically here tend to cluster in a distinct region of the NDM, which predominantly exhibit hydrophilic properties. And virtually no area of this drug-related space is untouched by food molecules, reflecting the extent to which many current drugs, of course, have been inspired by naturally occurring compounds, and also suggesting a vast untapped potential within the broader chemical landscape of food. So if you look into this part of the plot, compared to drug classes such as, for example, adrenergic antagonists that I'm showing here, which cluster in a well-defined region and are often developed with me-too chemistry that involves basically iterative modification of existing compounds. Food molecules, so let's look in here, that have been shaped by millions of years of evolution display, let's say, a higher chemical diversity, allowing them to interact with a wider array of protein targets. And so we like to think about this food compound as evolving in a dynamic ecosystems where they varied in concentration and competed for different biological targets. So this is a key difference with drugs. So consequently, food molecules often provide chemical scaffolds optimized for protein binding, while simultaneously demonstrating a broader range of structures and features. So this is really what we see, for example, for polyphenols in panel C. And a similar analysis will allow us to study the behavior of toxins, pollutants, and artificial food chemicals compared to naturally occurring compounds in food. So now we will dig deeper into how the variability of chemical concentration, a key feature of chemicals, is not noise, but is rather informative. Indeed, I will show you how by analyzing the statistical patterns observed in food composition data, we can create tools to characterize the food supply quality. So at the beginning of our journey, we ask ourselves a very simple question. We are physicists, aren't we? So how much nutrient is in a food? So we started by collecting the nutrient profile of all foods in the American food supply, but also we look into other food supplies. And here, for example, you see the nutritional profile of raw onion as reported by the USDA. So these are concentration per 100 grams, so grams per 100 grams. And we see that they cover 8 orders of magnitude, a range that is driven by the complexity of biochemical processes responsible for nutrient production and modulation. So it's closer to biological systems than to standard food composition. So we proceeded in studying how each single nutrient is distributed across the food supply, as plotted here for vitamin B12, thiamine, zinc, gadolinic acid, and total protein. So the probability Q that you read here captured the food source variability for a single nutrient, yet we haven't found any guidance about its expected functional form. This is what physicists look for. So despite the noise and batch effect, because I think we all know that food supplies, so the US food supply specifically, is not a random sample of foods, we saw a common pattern emerging that you can see here. So long story very short, there's a lot of math here. Each nutrient seems to be characterized by a similar functional form in the log space, only translated at different average level of concentration. So we find that log normals with similar logarithmic standard deviation seem to best describe the observed distribution, allowing us to do what we do here in this corner to rescale all nutrients and compare them on a single plot. So moreover, we have also observed a cleaner behavior for simple ingredients like fruit and vegetables, and we have also recently confirmed the results in metabolomics experiments with Michael, and these results are already available on bioRxiv. So the observed common scale of fluctuation in the log space followed by all nutrients suggests a methodology to detect outliers. So the patterns of different nutrient outlier is then informative of the type and extent of processing, as we can appreciate here with different versions of onion. So this implies we have found a natural metric of processing that is not just a matter of presence and absence of additives, that is usually the standard metric. So our findings connect to the increasing attention to ultra-processed food in scientific literature, very hot topic. So while the name ultra-processed food comes from the most common classification system used in epidemiology, that is NOVA, scientists do not agree on a unique way of talking about this. And this is why many researchers are now pushing for the term highly processed food. This represents a paradigm shift in nutrition science, offering, I would say, a complex system perspective on assessing food quality. However, defining highly processed food remains controversial, primarily due to the need for deeper fundamental research and better data on food composition and processing. And to fully map the involved biological mechanism is more than one, right? And I would also add a more data-driven culture in nutritional epidemiology. So in some of these foods, not only the standard chemicals that we observed before are in weird proportion and combination, as we've seen in the Z-score plot, but there are also many, let's call them alien chemicals that like additives. So according to our observation, there is a clear chemical physical fingerprints characterizing ultra-processed food that implies that food processing systematically and reproducibly, a very important word, alters the nutrient concentration in food, making an ideal application for machine learning. So understanding food processing and scoring it in a scalable and reproducible fashion has reached the public audience debate. Okay, and as you can read here in a recent article in Time magazine about the issue, or actually talking about ultra-processed foods. So leveraging the patterns of nutrient alteration in food, we created a score, FPRO, based on the prediction of a random forest algorithm projected on a one-dimensional space, so a bit of linear algebra fun. So this algorithm takes as input nutrient concentration, and as you can see here, we were able to score very quickly a sample of the US food supply ranked by FPRO. Okay, so the score is in good agreement with classification like NOVA, as we can see on the right, by following the colors. So unprocessed here, processed and ultra processed. However, look at this part of the plot, right? Nutrient concentration, working with nutrient concentration, give us more granularity, allowing us to discriminate between products, more or less 70% of the food supply that otherwise would be considered identical. So, and moreover, we can follow the progressive alteration of ingredients such as onion from raw to extremely, let's say, processed. So the algorithm is fast, and the most important part is that it adapts to different sizes of the nutrient panel, from nutrition facts, so the minimal information, really what we have, right, up to hundreds of nutrients when there is availability. So why having a continuous score is important? Because we can study the variability characterizing different food categories and suggest alternatives within the same group without drastically changing the dietary patterns of an individual. So indeed, humans, there were studies about this, tend to choose within a limited number of food categories, and our diet is better captured by this level of granularity. So this type of diet modeling led to, in the US, to what we call the what we eat in America classes. So these are groups of foods with similar nutrient content and usage. The reality is that there is a lot of variability, as you can see here. So here I'm showing basically the classes ranked by median processing score. For example, if we look into the ready-to-eat cereals, we observe an increase in patterns of FPRO determined by several nutrients alteration, like decrease of fiber content, sugar addition, fat addition, and vitamin and mineral fortification. So these cereals reported here are considered equally ultra-processed by NOVA, for example. So before implementing a food substitution strategy, we investigated the association of our score with several phenotypes. First, we extended our score, a measure for single foods, to a measure for the overall diet. We created two schemes, a gram-based version that is very important to test the chemical exposure, association with chemical exposures, and a calorie-based one. Okay, these are here. So we tested this measure in an environment-wide association study, or EWAS. It's very similar to GWAS in genomics, comprising more than 400 different phenotypes, from biological aging to vitamin bioavailability and metabolic syndrome, providing quite remarkable predictive power. So once quantified the association between FPRO and health phenotypes, we implemented an isocaloric substitution strategy, fixing the food categories consumed by each individual to limit the impact on their diet. So to minimize the dietary shift required, we'd identify basically within each diet the items with high caloric contribution and for which there is a significant less processed alternative within the same group. So by changing, let's look into here, by changing one single item per person, we already see results. And overall, we see a shift on how processes the individual diet of Americans, but we can also estimate the implication for odds of metabolic syndrome, the viability of vitamins, and the concentration of contaminants like bisphenol A in the urines. So to implement this in real life, it's a toy model, of course. One consumer should be empowered with information on the degree of processing characterizing the foods that we buy and the available alternatives. So building on this idea, during the pandemic, we were a little bit bored, and so we decided to mine the website of three major grocery stores, collecting more than 50K products with nutrition facts and ingredient list, and we calculated their FPRO. This is what you find in GroceryDB that has been recently accepted in Nature Food. So this is our pilot currently available at truefood.tech. And so we are always following this idea of minimal food substitution strategy. And you can see here that basically foods are classified, are reported into classes, and substitution happens and suggestion happens at the class level. So to introduce you to the score, I compare here two products, right? Two cheesecakes. So you can see their nutrition facts compared, and the lines basically tell you where they are compared to other products in the same category for calories and sugar. Be mindful that this score here is a percentile related to the cake category. So the absolute score here tells you that we're close to 1. That means that we're definitely not talking about raw ingredients, or we are not talking about carrots, right? So we have access also to the ingredient list that we structure as 3. There is a lot of information that we can mine from the ingredient list, but the quality of the data is actually worse than the nutrition facts. And so there is a lot of work that will go into this to actually get more chemical composition out of it. And I would like to highlight basically appreciate the complexity, please, of the second cake compared to the first one. So even the complexity of this tree is actually a score for food processing. We highlight also the presence of additives in red as classified by the FDA, but of course this can be made international. And finally, if you selected the second cake, we offer less processed alternative within the same category. So while FPRO offers a very simple solution, working with minimal standardized information available in nutrition facts, we can and we should do better and move away also from NOVA. This is exactly what we're currently doing, curating an international food composition database with lingual annotations for detailed food processing labels, and using it for the fine-tuning of a birth language model that will allow us to predict food processing labels for big population studies and quantify the epidemiological relevance of specific combination of food processing label for specific food groups. So this is a lot of information to process, but in other words, so look at the number of people we have and we put together. We are trying to quantify the health consequences of food matrix alterations at scale. So please stay tuned. And so we're done for today's talk. I'm aware I've exposed you to a lot of notion from different fields. So this is basically the 2 main branches of the Foodome project, a lot about the chemical characterization of the bioactivity of food molecules here, and a lot of AI-driven public health intervention here. And I don't do this alone, but with a team of people. These are the people working with me. You will hear also from Michael, and a big thank you to our funding agencies, so the Brigham and Women's Hospital, NIH, and the American Heart Association, and of course to my mentors, Joe Luscals and Laszlo Barabaj. Thank you.
Thank you, Julia. Thank you, Julia. We now entered a hardcore physics and nutrition course, but I think I wanted to draw attention to how, in a different scientific domain, how the similar tools could be used differently and give insight into our field from a slightly different angle. And I think this is something which we need to do more, to borrow ideas from other scientific domains. Now, questions to Julia. I have one, if no one dares to ask a question. So I just wanted to ask you, Julia, if you could give us a 1-minute elevator pitch on the machine learning or AI applications used during the FPRO development. So what was the algorithms behind?
Very simple. So actually we tested multiple ones, from random forest, so tree-based algorithms, XGBoost, up to different type of neural networks, and actually found that random forest worked very, very fine. And so initially we basically use, so we went with the simplest thing, because to me, the simple is always the best if it performs in a very simple, in a comparable way. And to be honest, what we realize is that while we can easily predict NOVA classification, but even other type of food classification from the correlated nutrient content, right? So that's really what machine learning does. It was not really the end point of our paper, right? Our paper actually showed that not only there is in the nutritional information, there is a lot of content that can be used in a correlated fashion to predict some of these labels that mention many times that they do not use nutrition facts at all. So first of all, biases of the researchers. But beyond that, you want to kind of even show limitation of classification, current classification methodologies, right? Because somehow what we showed is that classes, at least food classes for processing, are able to be, let's say, fairly assigned just to a limited number of foods. Everything else is somehow speculation. And the algorithm shows this to you very, 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 in a very clear way, right? So starting from that and realizing that yes, we were able to mimic basically the classification process, then we said, okay, well, let me use basically how certain is this algorithm for classifying food classes that are, for classifying foods that are usually not very well classified by, let's say, experts. And let's basically create a score that is able to balance basically this uncertainty, right? So this is the linear algebra part that I was mentioning. So with that, we actually created something that is way more flexible, way more reproducible, and is informative, right? So we can do much better, and that's what we are currently doing with somehow language model, but I really like the quick and clean and elegant type of solutions as well.
Yeah, thank you, Julia. And also just draw your attention that these are very simple machine learning models, and we not necessarily need large language models to solve everything. So that's also a message, I think. Okay, good. No more questions. Thank you, Julia. Now we switch to Michael.
Thank you.
And I already started to introduce Michael, but I won't do it again. So Michael from Northeastern University, Boston, please, the floor is yours.
Yeah. Okay. You can see my slides. Everything's good. Cool. Okay, so I'm going to talk a little bit about what happens after the data extraction that we saw earlier by Tome, right? How can we take these lists and activate them and extract health-related information from those things? And so what we have is you can take data from different sources, databases, extraction from literature, genomics, and experimental results, and you can get a collection of data for any particular food item. And here in this example, I'm using apple. And we can collect and extract almost 9,000 compounds for apple. And what we can see is the breakdown of them. About half of them are observed, the other half are inferred. And then FoodDB assigns about 800 health effects for those compounds. And the USDA tracks only 56 of those compounds and their quantities, right? And so what we can see from here is that if we want to find the health effects of more compounds within a food item, we need to be able to leverage some technologies that we can take from, say, like drug development as a way to find health compounds for those health effects for those compounds. And so how can we do that? Well, one of the first steps that we have is like that we need to understand is how do food compounds impact our health? And so this is taken from the paper that Julia discussed earlier on the unpacked chemical complexity, where we track, say, a well-reported pathway here of how choline goes through our body, right? Choline can be taken by the gut microbiome and converted into TMA, which then the liver will convert into TMAO, which will interact with proteins in our body to cause heart disease, right? And so what we can learn from this is that the way that food compounds interact with our body are complex, and our behaviors can also affect these pathways. For example, if we have a dish where we are introducing other compounds from other ingredients here, garlic and red wine, we can actually deactivate certain pathways with the compounds in those foods as well, as in this example here, where allicin and DMB will interfere with the conversion of choline into to TMA. So the way that food compounds behave in our body is very complex, yet we can take some inspirations from drug development, as I said before, where what they do when looking at how to treat diseases is they look at, say, the compound protein interactions that are occurring. At the end of this plot, that cause the disease, and they treat there, right? And while also trying to control for the upstream effects of, say, the liver or the gut microbiota. And so using this as inspiration, we were looking at how can we apply this type of methodology to food compounds. And so the first thing that we did was try to look for compound protein interactions for food compounds. And so we developed a package, CPI extract, where we can input a compound and it searches 9 different compound protein databases to extract out the binding information, as you can see on the left. Now, these databases are highly heterogeneous, and the data is highly scattered as well. And so the package is able to automate and harmonize this stuff into a single output for us to use. Now, when we use this on food compounds, what we see is that the nutrient dark matter is largely understudied. For example, here, where if we just take FoodDB compounds, the almost 71,000 compounds that are in FoodDB, and run it through our pipeline, only 3,600 of them do we find at least one interaction within these data sets, saying that if we want to apply or find health effects for these compounds, we need to apply some sort of AI prediction algorithms to extend health effects beyond what is already known. And so, again, this is not a new problem, as pharmaceutical development commonly runs into this problem. There is a lack of interactions within drugs. Like if they propose a new drug, they have to be able to try to determine or try to predict how that drug is going to interact with the body in some way. And therefore, drug development has already established a lot of AI technologies and pipelines that we can try to leverage for food compounds as a way to predict health effects. The very first of these is pre-screening based on bioavailability. There are open source ones, as well as pharmaceuticals probably have their own internal ones as well. But the two that I'm going to show here is Swiss ADME and AdmetLab 3, which when you give it a compound, it will try to predict whether or not that compound is absorbed, distributed through the body, if it can be broken down by the liver, how long it's in the body, as well as it can try to predict, say, a maximum dosage. There's a concentration prediction as well. And these models are trained on measured values for drugs, existing values for drugs, and the structural similarity of compounds to predict the values for new compounds. Furthermore, drug discovery will try to predict compound protein interactions as well as a pre-screening, where it also is using the structure of the compound, the structure of the protein, and existing compound protein interaction data to predict a binding of a new drug. And then after they do a pre-screen with this AI pipeline, they end up going further into simulating the physical interaction between the protein and the compound within a docking algorithm. Here, it's AutoDock-Vino. But there are many different types of docking algorithms. And then they'll go into, say, experimental, where they do in vitro bioassays examining these interactions, maybe with structurally similar compounds, even before they start to develop the drug itself, because the cost of developing the drug is so large. And so what we're going to focus on now is just the AI pre-screening section of this on the left, and trying to apply this to food compounds. And so when we take these AI models and try to run them, what we find is that there is a lack of negatives or non-interaction data within these data sets, for example, binding DB. And this lack of negatives means that there's an imbalance between positive CPI, compound protein interactions, and negative CPI. And this causes a lot of false positives and false negatives, as we see on the left here, where the AI tool is learning a shortcut rather than learning some features. And to try to prove this, what we did was we built a network of CPI data where the nodes are the proteins and the compounds over here, and the links are the confirmed interactions between them. And using this network, we were able to build a configuration model that just uses the properties of the network and trying to learn or try to predict CPI from just the network. And what we see is that if we look at deep purpose, the AI model versus our configuration model, they give similar performances. This suggests to us that the deep purpose model, this AI model, is not actually using the structure, compound structure, or the protein structure metadata in the training. More so, it's actually learning the connectivity of the proteins and the compounds within the network to make its predictions. And so in order to fix this, what we observed within our network is that as you get further away from the node of interest, you actually start to see a lowering in the binding affinity. So when you start hopping away, so like if you are interested in serine racemase as your protein of interest, the further hops away that you go from this interest, the binding affinity goes down. And what we can see here is that eventually, as we get far enough away, we start to cross this threshold here, this dotted line. This is what is commonly used in drug development. Anything below this line is typically considered to be things that have significant binding potential to be used as a drug. Whereas if it's above this line, the binding is too sporadic or too weak in order to cause any signal to occur within the body, right? And so using this, we can use this hop distance as a measure to start adding network-derived negatives to fix the imbalance of deep purpose, which is what we do next here. And as we can see that if we just use the configuration model that we had before, and then we use the network-derived negatives with deep purpose, we see an improvement in AUC as it starts to learn some of the additional metadata, say the structure of the compound or the structure of the protein, as a way to predict CPI information. And furthermore, if you are to increase the space, the embedding space of not just the compounds that were within binding DB, but also include the entire corpus of compounds within PubChem or proteins within Protein Data Bank, it can learn a much fuller representation of the chemical space and the protein space, which also boosts performance. More importantly for us in the food space is that when we look at these models and we compare its predictive performance for drugs versus natural compounds that we find in food, this is using the nutrient dark matter, what we see is that there is not a drop in performance, suggesting that these models that are being trained on drugs can be used on food compounds. And as Julia was showing before, is that a lot of the drugs in the food compounds actually share a similar space, as the natural compounds are the building blocks of drugs, are the inspiration for a lot of drugs. And so using this to conclude here, what we are proposing now is a way that we can systematically run the nutrient dark matter through an assortment of AI models to uncover potential health effects and maybe create some actionable insights for nutritional studies beyond the food compounds that are currently studied within a lot of the literature. And so you can take the data from many databases, run it through Swiss ADME or ADMET lab to get whether or not it is absorbed by the body. And then the ones that are absorbed by the body, we can then put into CPI extract to get its compound protein interactions, as well as put into AI bind to get predicted interactions that then we can run through packages like the one that we are developing in the lab, NetMedPy, which does network medicine-based approaches to make predictions about which health effects those compounds are going to impact. And here, NetMedPy is a package that does large-scale screening for this. So we can run the entire nutrient dark matter through this to try to find health effects for not just stuff that is commonly studied. And with that, I'll conclude my talk. I would like to thank EFSA for inviting me, as well as the team at the Network Science Institute and my collaborators at Network Science Institute for the research that we're doing there. Mentors like Laszlo Verbassi and Giulia Menichetti, which you talked about before, and as well as Andres and Gordana, the other two postdocs that I work with, and the students that worked on the projects. And this is the literature that I discussed today in this talk. Thank you.
Thank you, Michael. Thank you for guiding us through a deeper and deeper series of algorithms. And I think that tells a lot how big a perspective it is, I think, for the food science to take up AI machine learning models and to go beyond the current understanding what we have. Questions? Yes.
Maybe, thank you for the presentation. You mentioned in one slide that the model was making shortcuts.
Yeah.
And I'd like to know how you identified them and what sort of were the steps to understand those.
Okay. So the identification really just comes down to the fact that when applying a machine learning model or any model, the balance of the data set, right, of the two classes matters a lot on whether or not the model can learn correctly. And a lot of people that make models for CPI prediction, they'll just randomly select some stuff, and they're not actively balancing there. So the red flag to us for whether or not that it was there or not was just how many positives and negatives were present in the training data set. That was the red flag to us to even look at it. And once we observed that, as we come from, I guess, a network space, we were looking at it as to try to correct for this through a network-based approach, right? As the CPI just naturally makes a network. Yeah.
Thank you. I think that also points to some kind of a message that we still need, and most probably will need for a long time, human in the loop, so the experts, and to see the red flags and to intervene and to make sure that the predictions, the learnings are right, but also to understand that maybe what a model learns and predicts, how it is new, maybe, and to apply this novelty into other areas. So I think that's a lot to explore or discover here as well. Thanks, Michael. Any more questions? No, we are very...
Sorry, can I add?
Yeah, Giulia, please.
Can I add just one thing? Yeah, no, and what you said is very important. And I think also it's not just having humans in the loop, it's also having a toolkit of different models, because really this is part of the things that Michael showed to you are showing how it was very important for us to, again, have a very simple model that we called in the presentation configuration model that disregards anything about structural information. If you see a dumb model like that one, that is very simple to implement for network scientists, but I think I would say also for the general audience and general public, if it performs exactly as your super fancy AI model, well, that's a problem. Unfortunately, this idea of having multiple models and always compare and having different type of, let's say, null hypothesis implemented is something typical of statistics and physics rather than computer science. So again, it's always a matter of building this type of bridges and having a multidisciplinary team.
Yeah,
Thank you.
and to further expand onto that, one of the things that we did do is, like, when you build a model, you should interrogate your model. We ended up taking the labels and the structures of the proteins and the compounds and shuffling them and applying them to different nodes to see if we could see a drop in performance as well. So interrogate the model after it's built as well, and you can find some issues.
Thanks, Michael. Thank you very much. And I think we need to close now because we are reaching into the coffee break very well. So thank you, Michael. Thank you, Julia, for being with us. And thanks for the audience. Yeah. And thanks, everyone, for staying with us. And now coffee break and then the closing session. Thanks.
Thank you, Akash.
Thanks.
Bye-bye.
Bye.
You know, I think when you were talking